So this is our last video before we start explaining some of the mysteries of quantum physics and relativity. Exciting. As we've seen before, in the second video, we are going to explain what state and simultaneity concepts are and why they are so useful. In the last video, we've seen that slide here, and we said we need to define the concept that we use, for instance, to define the TUP principle, measurement, space, time, energy. We've defined measurement. Now we have to talk about space and time. And for that, we need to define first what the state is and what simultaneity means. Okay, let's start with state. The state of an object particle is fundamental to understand modern physics, so that's very important that we understand what we're talking about here. Initially, it's an abstract concept, it can be mass, charge, position, momentum, all of this combined together, giving the state of a particle. And it's fairly abstract, but that's how you define a generic concept. Now, on the other hand, when you apply it to a very specific object or particle, then you have to assign values to those properties, So in other words, you have an abstract thing, like things like that, and then you will say, okay, I'm talking specifically about this one, and then I have to assign values to, the length, the mass, whatever. And if we think about it, it's very similar to the concept of vector, in the mathematical world. And of course, this is important because we're going to talk about isomorphism again, between physical world and mathematical world. So we have to understand that. But since this first series of videos is without math, let's just let me just remind you what the vector is, and we'll use only drawing. Forget about the math, So vector is just an abstract thing like this. It's basically an arrow like that. And the thing is, if we want to apply it to a specific vector, like this vector here, then we have to use a reference. And for that, if we're talking about a vector in a 3D space, like for instance, this space here, with height and width and depth, we need three vectors, three-dimensional three vectors. So let's assume we take those as a reference, we combine them together, it's called a basis, and then we apply that to measure this vector here in the mathematical world. And here, for instance, it will be 5 times the blue vector plus 3 times the red vector plus 2 times the green vector. Okay, something like this, which is even more clear. Now, because we use this specific reference here, we can therefore use those values to define the specific vector v here. It's not abstract anymore. It becomes something concrete with numbers, 3, 2, 5, which obviously correspond to these numbers here. But again, we didn't say equal because this is only true if we use this reference. Let's call them X, Y, and Z. But if we change those references, for instance, this one is in the other direction, this one is longer, this one is longer, then these numbers here will change. It will still be the same vector, though. But it's because we changed the reference, then the values that we will measure will be different. So again, when you go to specific things, you always have to take into account a reference. Okay? So this is what I meant by, similar to the concept of vector, because that's the case for the state as well. And again, this is why, the isomorphic equivalent to a state in the physical world will be a vector in the mathematical world. So funny. Now, talking about space and time. Well, space and time are part of this state. Sometimes you say it's a function. It's a function of time, but actually you can include time as one of the properties of the specific state you're looking at. And since they are part of the state, they must be observables, as we've seen previously in the other videos. And therefore, we should be able to measure their amplitude values, again, based on a reference. Okay, so these are the two things we need to remember here. for space and time. Now, the second thing after state we want to talk about here is simultaneity. Einstein used that concept to define special relativity or to explain special relativity. What he said is that, okay, we have two mirrors here, and there's a middle point between the two mirrors, and if there are lights coming here and there, if they arrive at the same time, then by definition, Einstein said, I will say that these two space-time events occurred simultaneously, and we're going to use something like that for our definition of simultaneity. Actually, it's the same thing, but will be a bit more accurate, I think. Of course, we're not trying to correct Einstein. He didn't need to be more accurate than that. It was sufficient to explain the thing. But in our case, we're going to talk about particles, quantum physics. So we need to be very precise and specific. And the first thing we need to do is to define what we mean by middle point here. Because Einstein said, it's the middle of the two. Okay, we understand what that means. But we really want, if we have not defined space nor time before, well, we have to define what the middle point here means, And that's fairly easy. You just generate the light, it goes like this, and then there are mirrors, and then if it comes back like that at the same time, then, okay, that means this is the middle point. So, piece of cake, always easy to define. But we, again, used a word which is not supposed to be there. We said at the same time. What does that mean at the same time? Because, time, we don't know what it is yet. We have not defined it, right? So let's do it in another way. What we say is that if two, lights arrive here, and here I can only detect one event, then I will say that these two space-time events were simultaneous. So, see, we didn't take any assumption about space or time or whatever. We just use light, and we'll see later why. And then from that, we could derive the middle point and also define the simultaneity concept. Okay, so now is the time to summarize, all these preliminary things that we needed in order to start our exploration and answer those questions and mysteries, about quantum physics and relativity. Okay, so the first thing is we have to focus on the physical world where we can measure things, and then find an isomorphic mathematical world, so that we can derive things in a logical way. Measurement is key to be able to define the states in the physical world and link them to the isomorphic vectors of the mathematical world. That's what we'll see in the next videos. And in both the physical world and the mathematical world measurements, which means assigning values to observable properties, all these imply the use of references. In the physical world, you need a reference to compare to, in order to define lengths and measure lengths and measure quantities, etc. And the same applies in the mathematical world, where you need a basis to assign values to the vectors you're going to use to represent the states, which will be isomorphic to the vectors in the mathematical world. Okay, and finally we need to define a minimal set of independent assumptions, such as the TUP that we saw before, and from which we can build up the whole model in a logical way, just a few basic assumptions, and then from there derive everything else. No holes, anywhere. Okay. By defining very precisely all the concepts we're going to use, like time, space, measurements, then we shall be able to do a lot of things. First, we can explain why we use certain math tools, Hilbert space vectors. Why Hilbert space vectors? Hermitian operators, why? Complex numbers. Why? Tensors. Tensors, magic tensors. Well, all of this we'll be able to understand, if we define very precisely what we're trying to achieve. Now, on the other hand, we'll also be able to explain, and that's, the main purpose also of this series of videos, the most mysterious paradoxes, in quantum physics and in relativity. And that's very exciting, things like the duality, of light being particle and wave at the same time. or Schrodinger's cat being dead and alive at the same time, superposition of states, or the wave function collapse, that's crazy. Anyway, so we'll be able to do that. And finally, to describe the universe rules, how we can define in the mathematical world how things work in the physical world. And the nice thing is that we'll show how to derive them from, very minimal number of assumptions. And, for example, of course, starting with a TUP, with a TUP, you can derive things like Newton's laws, Maxwell equations, yes, quantum mechanics, general relativity. All of this from a simple principle, the TUP that we saw before. And more than that, we'll be able to answer questions like, what happened before the Big Bang? Yeah, is the universe infinite or is it finite? Oh, and more than that. So, you need some patience, but it's worth it. So I'll see you in the next video.